All right, welcome back, everyone. For our final session, it's my great pleasure to introduce Bertrand Lasternas, Senior Researcher for the Center for Building Performance and Diagnostics at Carnegie Mellon University, and his topic is, Shh, listen, your building is telling you something. Welcome, Bertrand.
Sorry. There you go. Thank you. First, I want to apologize for, even after 5 years in the US, in Pittsburgh, I still have a terrible French accent. So, sorry about this. Speaking about France, everybody know right now in Paris, that's the COP21, this big climate talk, how to save the world, how to reduce our energy consumption. Just for a fact, US building, commercial, and residential buildings consume about 41% of the overall energy consumption of this country. So if you want to start acting on this, buildings is one of your best bets. Okay, a little bit of background about CMU. It's about 100 years old university, about 13,000 students. Half of them are undergraduates. We spend about $20 million a year on our utility budget. It's about $1,600 per year per student. So a pretty big number. The goal, one of the goals of CMU, which is part of this Oakland 2030 district, is to save 50% of the campus energy consumption by 2030. So it's a pretty big, pretty challenging goal. Talking about big data, we have a 6.5 million square feet campus, 65 plus building, which represent about 80,000 data points, streaming data about each minute or down to each seconds. So it's a lot of data. So everything will be around energy and how to use big data to save energy, to be more energy efficient. This first question is why we didn't save energy before. First, we had no idea what we were using. We don't have data. We don't measure it, so we cannot know what's happening. Because we don't have data, we cannot quantify it. You don't have data, you cannot quantify, so you don't know where to start. What should I do first to save energy? What is the easiest way? What is the most cost-effective way to start saving energy? And we didn't know numbers. When you buy a computer, when you buy a car, you will have a list of different metrics. Gas, miles per gallon, all this kind of stuff, or CPU or rates. In buildings, you will have the square footage, the building class, and that's about it. No metrics telling you this is a good building, this is a good hotel, this is an energy-efficient hotel, this is a very bad hotel. So the challenge, collect all of this data, a lot of data, monitor, diagnose, and optimize the building performance with this new data, predict fault, failure. The solution, few of the solutions use advanced machine learning. I think machine learning is one of the topics here in big data. Each time you talk about big data, you have to talk about machine learning. Predict, forecast energy data to make energy efficiency actions. So everything started about 5 years ago in this lab. If you go on the campus, on CMU campus, just right after the tennis court, you will see on top of this building the lab. So in this lab, we did a lot of integration, test of systems. And we came with this framework of what to do to achieve energy efficiency with big data in buildings. First, you have to integrate all of this information. You have to monitor and diagnose. And something we also came back with big data is how do you share this information? How do you display this information? How do you make sure everybody understands this information? So we have different ways to share this data at different levels. The first one will be facility manager executives, so the one who have the money to spend to retrofit a building, to go to next year retrofit actions. You have building occupants, the one in the building, the one living the building, the one feeding the buildings. And you will have the publics. Disclosure law. You should be able, everybody should be able to know what all Pittsburgh building consume. And then you want to give control back to the occupants. Give them the power to change their environment, control things, turn things on and off. So first, because you have so many data coming from different vendors, different manufacturers. You will have the lighting system, you will have the HVAC system, you will have the security system, the plug load system. All of them came from different vendors. They don't talk the same protocols. They don't have the same naming convention. So first you have to understand everything. What does this data mean? What is the meaning of all of this data? So we do some advanced machine learning to take the semantic out of the name and start to create patterns, the way all these points interact with each other. So we will create clusters of points, like all the VAVs or all the lights, because we can understand there are lights, we will group them together. And then we do some advanced machine learning to understand the relation between these systems. So if you have a big ventilation unit who supply air in this room, we'll be able to say this VAV is coming to this very specific room. To start to map all the different systems. And then once you understand what's happening, you have to put this data somewhere. So that's the overall architecture of this, where you have all the data points. Can be from you can light, the smart meters will give you this 15-minute time interval data. Can be real-time data at the second data interval. Can be building automation sensor like air quality sensor, humidity sensor, temperature sensor. It can be static data, size of the building, square footage of anything. You put this in the data. We work with some OSI soft PI systems, some DOE, Department of Energy database, open source database, and analyze this data and share this data with the public. Different way to share this data, different dashboard, different display to share this data. We can do this kind of graphics where you will have a piece of equipment. You will be able for a field engineer to go in front of this equipment and have real-time data, real-time diagnostic. So somebody, analogy with a car, you will be able to plug to the computer of your car and have a total diagnostic. Here you can basically do the same. Go plug to any systems and have a real-time information about the systems. And all of this creates a lot of data and you have to process. We do this with some advanced machine learning. So we push everything in the cloud. Everything is great in the cloud. Take all the computation, get the prediction back in our systems. So you can see all the loop to get the result back and display these results. Some experimentation to do fault diagnostic. So a few years ago, we were reactive maintenance. Something break, you go fix it. Now we can predict when something is going to fail. The example of my colleague in Carnegie Mellon who can predict Boeing airplane system failures. We can do the same in the buildings. So we could potentially know when one of these ventilation units is going to collapse and fix it before it. Reduce the cost, reduce the comfort, or increase the comfort of the occupants. We can display this in different ways. We can do temperature and energy prediction. So going back to the effort you can light and all this utility company try to predict in advance what will be the peak demand or the electricity price function of weather forecast. We can also do the same with advanced machine learning. We do this on campus. So this blue box, it's a real-time energy consumption of all of this building on campus. We don't do a 15-minute time interval. We do 1 second. So we are research, so we can play with numbers. So here, we receive each second the overall energy consumption of the buildings. Then we can predict and know that this building in 10 minutes will consume this amount of energy and understand why it's consuming this amount and act upon. Then we can control things back. Once you understand it, you know to better control it. But in order to control it, you need to give occupants control. So we did a lot of work with smartphone. And now, this is a picture of the lab. So you will go in our lab or some building on campus, and we'll have the real-time information about different metrics, different value, different sensors, temperature, CO2 particles. You will be able to control. You will point your device in front of the light, in front of the fan, in front of the windows, and click on it, and the window will open. That's what we envision for any buildings in the next 20 years. We did the same with plug loads. So buildings is becoming more efficient, but you will have a lot of different plug loads. Any computer, any laptop, any monitor, anything which is plugged to an outlet. These numbers keep increasing more and more. So in some high-efficiency building, 50% of the electrical consumption only came from the stuff you plug on the wall. So we did a lot of experimentation about giving feedback to the occupants with this kind of dashboard, with communication, expert consulting, so analyze the data, understand the pattern, give feedback to the occupant, letting them know that they kept their monitor on all night long. By turning off this when they leave the office could make them save 30%. We can allow them to control. They can forget something, but when they arrive at home, open the smartphone, turn off their laptop, turn off their screen, anything. Or do a more simple calendar. Everything goes off at 6 p.m., everything turned back on at 6 a.m. We did this. Maybe you learn about this with PNC Bank in one of the floor in downtown Pittsburgh. And we were able to save 40% of their electrical energy consumption on this floor. So pretty impressive. By giving them the full suite of feedback, control, and calendar. And then we wanted to learn, does this experimentation sustain in the time? If we remove everything, does occupants, does the employee understood something, and will keep the same behavior? So that's our baseline. That's 3 months of intervention, 40%. And then we remove everything, and we still measure for 3 more months. And they only overconsume by 5%. So overall, after 9 months of experimentation, they were saving 35% of their consumption. We also try to consider about IQ in the environmental quality. So how many of you feel this room is too cold? I would say about half and half. This is cold. It's cold outside. Why do you waste so much energy making this room at 72? Air quality, visual quality, acoustic quality, thermal quality. Going back to new toys, so going about IoT, Internet of Things, we keep producing more and more data. So we work with a Pittsburgh-based company, Maya Design, and they create what they call the Interstack. So you can plug and play and start to create your own system who can store data, collect data, measure data, and share this data. So this is what we used to measure all this information 5 years ago. So you can see it's printed circuit board with kind of ugly, with a lot of wires. Something break here, we basically have to redo everything, cost us a few $1,000s. This is replaced by this. This can collect 5 sensors. I now need to collect 5 more sensors. I just stack something in between, and now I can collect everything. So building in big data is, in my sense, very important, and I think it will become more and more important. As this building will produce more and more data, you will have a lot of insight if you start to understand this data, collect this data, and share this data with the occupants. That's it.